Hello everyone, welcome to my YouTube channel, The Physicist. So in this video, we are going to discuss the electromagnetic theory of light and also the quantum theory of light. Okay, so let us first discuss the electromagnetic theory of light. The electromagnetic theory of light. Okay, this is also called, we can also say for short, EM theory. E for electro and M for magnetic. Okay, so when we look at the word electromagnetic, it is formed using two words, electro, which is come from electricity. Okay, this is associated with current, charge, okay, and magnetic. Okay, these two words form electromagnetic. So magnetic is come from magnetism. Okay, these are also produced by currents, that is moving charge. Okay, so that's why these are called electromagnetic, because electric and magnetic field are involved in it. Okay, so how we came about this theory, electromagnetic theory, let us discuss. So the 19th century saw the development of electricity and magnetism separately. Okay, so in 1820, Oersted discovered the current effects. Oersted discovered that the current produces magnetic effects. Okay, and at the same time, around the same time, the Ampere found that the two parallel wires carrying current attracts each other. Okay, and in 1830, Michael Faraday, he carried out experiment which showed that varying magnetic field induces an electromagnetic or electromotive force. Okay, and similar experiment were carried out by the Henry around the same time. So now we know the law which is given the name of Faraday and Henry, called the Faraday-Henry law. Okay, and soon afterward, the Maxwell generalized the Ampere's law by stating that changing electric field can produce magnetic field. Okay, he summed up his laws and all the laws of electricity and magnetism in the form of four equations, which we now refer as the Maxwell equations. Okay, from these equations he derived the wave equations for electric and magnetic fields. Okay, and from these wave equations he could derive from these equations we could derive that the velocity of electromagnetic waves can be calculated. Okay, using the experiment in which a certain quantity of electric charge is measured by two different methods, and these measurements were carried out in 1856 by Collarge and Weber. Okay, they carried out these experiments about the velocity of electromagnetic waves, and from their data Maxwell found that the speed of electromagnetic wave in air should be about, so speed of EM waves in air should be about 3.107 times 10 raised to power 8 meters per second. Okay, and he found that the values is very close to the measured value of speed of light, okay, which was measured by the Fizeau. So the speed of light was measured by the Fizeau in 1849, and he found that it was the most accurate or precise value of the speed of light. So the speed of light was found out to be 3.14858 into 10 raised to power 8 meters per second. Okay, and from these two values that were very close to each other, this led Maxwell to propound his famous electromagnetic theory of light. So he said that according to which light waves are nothing but electromagnetic waves. Okay, so he said that light is also a electromagnetic wave. Okay, so different colors of light, different which we can see is nothing but the electromagnetic waves. Okay, so associated with a light wave are the changing electric and magnetic fields. Okay, the changing magnetic field, for example, the changing magnetic field produces a time and space varying electric field, and also changing electric field can produce a time and space varying magnetic field. Okay, and this result in propagation of propagation of the electromagnetic wave. So due to this, these waves can even travel in free space, that is in vacuum. And in 1888, Hertz carried out experiments which could produce and detect electromagnetic waves of frequency that were smaller than those of light, and these waves were produced by discharging electrically charged plates through a spark gap. The frequency of the emitted electromagnetic wave depend upon the value of inductance and capacitance that were used in the circuit. Okay, and Hertz also produced standing electromagnetic waves. Okay, standing electromagnetic waves. How he did so? By getting them reflected by metal sheets. So he took two metal sheets and he get them reflected by these two metal sheets. So he produced standing electromagnetic waves like that on a string which is stored on a between two end walls. Okay, so he could calculate the wavelength of waves, and knowing the frequency he showed that speed of electromagnetic waves was same as the speed of the light. Okay, and using a collimated electromagnetic wave and getting it reflected by metal sheets, he could demonstrate the laws of reflections, right? So Hertz experiment results provided a dramatic confirmation of the Maxwell electromagnetic theory. In addition, there were so many other experimental results which were quantitatively explained by the Maxwell theory that toward the end of the 19th century, physicists thought that one had finally understood what light really was. But to the contrary, it was found that this is not the case. We still don't know what light actually is. This is leading us to the other theory of light, which is the quantum theory of light. Okay, the quantum theory of light. So let us discuss the quantum theory of light. Okay, so in 1887, Henry Hertz, the same person who discovered that the who confirmed the electromagnetic theory of light, he discovered that a metal irradiated by a light beam would emit electrons if the frequency of radiation were above a certain critical value. Okay, this phenomena is known as the photoelectric effect. Okay, and cannot be explained by the theory based on the wave model of light. Okay, so Einstein in 1905, okay, Einstein gave the interpret this photoelectric effect by putting forward his famous photon theory, according to which the energy in light beam, so energy in a light beam of frequency nu was concentrated in corpuscles of energy h nu, where h is the Planck's constant. In 1905 paper, Einstein wrote, according to Maxwell theory, energy is considered to be continuous spatial function of all purely electromagnetic phenomena, hence also for light. The wave theory of light, which operates with continuous spatial functions, has provided itself superbly in describing purely optical phenomena and will probably never be replaced by another theory. So one should keep in mind, however, that optical observation refer to the time average rather than instantaneous values. And it is quite conceivable, despite the complete confirmation of theory of diffraction, reflection, refraction, dispersion, etc. by experiment, that the theory of light operating with continuous spatial functions leads to contradiction when applied to phenomena of emission and transformation of light. Indeed, it seems to me that observations of black body radiation, photoluminescence, production of cathode rays by ultraviolet light, and other related phenomena associated with the emission or transformation of light appear more rapidly understood if one assumes that the energy of light is discontinuously distributed in space. So, according to the assumption considered here, in the propagation of the light ray emitted from a point source, the energy is not distributed continuously over ever increasing volume of space, but consists of finite number of energy quanta localized at points of space that move without dividing and can be absorbed or generated only as complete units. In this paper, I with to present the train of thought and cite the facts that led me onto this path in the hope that approaches to present will prove of use to some researcher in their investigation. So that were the the para that Einstein wrote is in paper. And we also mention here that it was only in 1926 that Gilbert Lewis, so in 1926 Gilbert Lewis, Gilbert Lewis, who was an American chemist, coined the word photon. So he used the word photon to describe the Einstein's localized energy quanta. So Einstein received the Nobel Prize in 1921 for this for this discovery of the law of photoelectric effect, and not for his theory of relativity. So Einstein photon theory predicted that if the frequency nu of the incident radiation was greater than a critical frequency called the threshold frequency, then the kinetic energy of the electron would be h times nu minus nu c. Okay, which was later verified by the Milken. Okay, for visible light, and then by de Broglie for X-rays. Okay, X-rays, and then by Thiebaud and Alice for gamma rays. Okay, Einstein also showed that the photon, in addition to having energy, so energy was equal to h nu. So in addition to having energy h nu, they should have momentum. So these photons have momentum which is equal to h nu by c, which was experimentally verified in 1923 by Compton. Okay, and this experiment was known as the Compton effect. And Compton in 1927, so 1927, he explained it in 1923, and in 1927 he received a Nobel Prize for this. Okay, so it may be mentioned here that in 1900 Max Planck had put forward his famous theory of black body radiation. Max Planck, on whose name this h is called the Planck's constant. Okay, so he put forward his famous theory of black body radiation and derived a derivation in which he considered that energy can be absorbed and emitted by individual resonators in quanta of magnitude h nu only. Okay, so he was the first to think light as when interacting with matter, it interact in as a particle. Okay, so what light actually is? So the question again is what light actually is. So we can say that, and according to Richard Feynman, it is neither. It's not. It's neither wave nor particle. Okay, it does what it does. Okay, we cannot say it is a particle or it is a wave. Okay, a light does what it does. Okay, In some experiments it shows its particle properties, and in some experiment it shows it wave properties. Okay, so we can say that it's neither. Okay, so this is all about light. Okay, in the next videos we will discuss some other things, other basic things. Okay, so thank you.